Good afternoon to each and everyone, especially to our instructor, Dr. Raymond A. Indangan. Sir, good afternoon. This is Math 305 Real Analysis and I am Nika Isdawaling for today's reporter. So, my topic for today is all about in section 10.2 Improper and Lebesgue integrals. In 10.2.1 Hicks theorem, if f from AB approaches to real numbers, then f is an element to R asterisk AB if and only if for every gamma is an element to AB, the restriction of f to A gamma belongs to R asterisk A gamma, and the equation 2, the limit from gamma approaches to the left integral from a to gamma f is equal to a is an element to real numbers. In this case, the integral from a to b f is equal to a. The idea of the proof of the part of this result is to take an increasing sequence gamma n converging to b so that f is an element to R asterisk a gamma n and limit sub n is an integral from a to gamma n if is equal to a. In order to show that f is an element to R asterisk ab, we need to construct gauge on AB. This is done by carefully piecing together gauge that work for the intervals gamma sub I minus 1, gamma sub I to obtain a gauge on AB. Since the details of this construction are somewhat delicate and not particularly informative, we will not go through them here but refer the reader to MTI. It is important to understand the significance of Hicks theorem. It implies that the generalized Riemann integral cannot be extended by taking limits as in equation 2. Indeed, if a function f has the property that its restriction to every subinterval a gamma where gamma is an element to ab is generalized Riemann integrable and such that equation 2 holds, then f already belongs to R asterisk ab. An alternative way of expressing this fact is that the generalized Riemann integral does not need to be extended by taking such limits. One can test a function for integrability on AB by examining its behavior on subintervals a gamma, with gamma is less than to b, since it is usually difficult to establish that a function is an R asterisk AB by using definition 10.1.1. This fact gives us another tool for showing that a function is generalized Riemann integrable on AB. It is often useful to evaluate the integral of a function by using equation 2. 10.2.3 definition: a function f is an element to R asterisk AB such that f is an element to R asterisk AB is said to be Lebesgue integrable on AB. The collection of all Lebesgue integrable functions on AB is denoted by LAB. Note, the collection of all Lebesgue integrable function is usually introduced in a totally different manner. One of the advantages of the generalized Riemann integral is that it includes the collection of Lebesgue integrable functions as a special and easily identifiable collection of functions. It is clear that if f is an element to R asterisk AB and if f of x is greater than or equal to 0 for all x is an element to AB, then we have f is equal to f is an element to R asterisk AB, so that f is an element to LAB, that is a non-negative function. F is an element to R asterisk AB belongs to LAB. The next result gives a more powerful test for a function in R asterisk AB to belong to LAB. 10.2.4 comparison test: if f omega is an element to R asterisk AB and the absolute value of f of x is less than or equal to omega of x for all x is an element to AB, then f is an element to LAB. And in equation 3, the absolute value of the integral from a to b f is less than or equal to the in equation 3, the integral from a to b, the absolute value of f is greater than or equal from the absolute value of the integral from a to b f, but less than or equal from the integral from a to b omega. Partial proof. The fact that f is an element to R asterisk AB is proved in MTI since f is greater than or equal to 0. This implies that f is an element to LAB. To establish equation 3, we note that f is greater than or equal to negative absolute of f but less than or equal to absolute value of f, and 10.1.5c imply that the integral from a to b f is greater than or equal to negative the integral from a to b absolute value of f but less than or equal from the integral from a to b the absolute value of f. Whence the first inequality in equation 3 follows, the second inequality follows from another application of 10.1.5 CQED. 10.2.5 theorem: if f, j is an element to LAB and if c is an element to real numbers, then CF and f plus g also belong to LAB. Moreover, in equation 4, the integral from a to b CF is equal to c, the integral from a to b f, and the integral from a to b is an absolute value of f plus j is less than or equal from the integral from a to b absolute value of f plus the integral from a to b absolute value of g. Proof: since the absolute value of c f of x is equal to the absolute value of c, the absolute value of f of x for all x is an element to AB. The hypothesis that f belongs to R asterisk AB implies that CF and the absolute value of CF also belongs to R at asterisk AB. When CF is an element to LAB, the triangle inequality implies that the absolute value of f of x plus g of x is less than or equal to the absolute value of f of x plus g of x for all x is an element to AB. But whence omega is equal to the absolute value of f plus the absolute value of g belongs to R asterisk AB, the comparison test 10.2.4 implies that f plus j belongs to LAB and that the integral from a to b, the absolute value of f plus j, is less than or equal from the integral from a to b of the quantity of the absolute value of f plus the absolute value of g is equal to the integral from a to b absolute value of f plus integral from a to b absolute value of g, QED. 10.2.6 theorem: if f is an element to R asterisk AB, the following assertions are equivalent. A. F is an element to LAB. B. There exists omega is an element to LAB such that f of x is less than or equal to omega of x for all x is an element to AB. C. There exists alpha is an element to LAB such that alpha of x is less than or equal to f of x for all x is an element to AB. Proof: in letter E, let omega is equal to f. Letter B, note that f is equal to omega minus omega minus f since omega minus f is greater than or equal to 0 and since omega minus f belongs to R asterisk AB, it follows that omega minus f is an element to LAB. Now apply theorem 10.2.5. We leave the proof that A implies C to the reader, QED. 10.2.7 theorem: if f, j is an element to LAB, then the function maximum of fg and the minimum fg also belongs to LAB. Proof. It follows from exercise 2.2.18 that if x is an element to AB, then the maximum f of x, g of x is equal to 1/2 the quantity of f of x plus g of x plus the absolute value of f of x minus g of x. The minimum f of x, g of x is equal to 1/2 of the absolute value of f of x, the quantity of f of x plus g of x minus the absolute value of f of x minus g of x. The assertions follow from these equations and theorem 10.2.5 QED. 10.2.8 theorem suppose that f, j, and alpha and omega belong to R asterisk AB if f is less than or equal to omega, j is less than or equal to omega, or if alpha is less than or equal to f and alpha is less than or equal to j, then max fg and minimum fg also belongs to R asterisk AB. Proof. Suppose that f is less than or equal to omega and j is less than or equal to omega, then the maximum fg is less than or equal to omega. It follows from the first equality in the proof of theorem 10.2.7 that 0 is less than or equal to the absolute value of f minus g is equal to 2 maximum f j minus f minus j less than or equal to 2 omega minus f minus g. Since 2 omega minus f minus g is greater than or equal to 0, this functions belongs to LAB. The comparison test 10.2.4 implies that 2 maximum fg minus f minus g belongs to LAB, and so maximum fg belongs to R asterisk AB. The second part of the assertion is proved similarly. QED. 10.2.9 definition. If f is an element to LAB, we define the semi-norm of f to be semi-norm of f is equal to the integral from a to b of f. If g is an element to LAB, we define the distance between f and g to be distance f and g is equal to the semi-norm of f minus g is equal to the integral from a to b, the absolute value of f minus g. We now establish a few properties of the semi-norm and distance functions. 10.2.10 theorem. The semi-norm function satisfies the semi-norm of f is greater than or equal to 0 for all f is an element to LAB. Number 2, if f of x is equal to 0 for x is an element AB, then the semi-norm of f is equal to 0. Number 3, if f is an element to LAB and c is an element to real numbers, then the semi-norm of CF is equal to the absolute value of c times the semi-norm of f. Number 4, if f g is an element to LAB, then the semi-norm of f plus g is less than or equal to the semi-norm of f plus the semi-norm of g. Proof. Parts 1, 2, 3 are easily seen. Part 4 follows that the fact that the absolute value of f plus j is less than or equal to the absolute value of f plus the absolute value of g, and theorem 10.1.5c QED. 10.2.11 theorem. The distance function satisfies number 1, distance fj is greater than or equal to 0 for all fj is an element to LAB. Number 2, if f of x is equal to j of x for x is an element AB, then distance fg is equal to 0. Number 3, distance fg is equal to distance jf for all fj is an element to LAB. Number 4, distance fh is less than or equal to distance fg plus distance gh for all fgh is an element to LAB. 10.2.12 Completeness Theorem. A sequence f sub n of functions in LAB converges to a functions f is an element to LAB if and only if it has the property that for every epsilon is greater than to 0, there exists h of epsilon such that if mn is greater than or equal to h of epsilon, then the semi-norm of f sub m minus f sub n is equal to the distance of f sub n is less than 2 epsilon. So that's all. Thank you for listening and God bless us all.